All right. Okay. So we are going to start chapter 9, and chapter 9 has a few different pieces with it. The first piece that we're going to look at is conic sections. All right. And we're going to look at these in the normal algebraic sense. And so we're going to ask ourselves, well, what is a conic section? A conic section is the intersection of a plane with a cone. Now, when I talk about a cone, I'm talking about an infinite cone. So if I were to draw this on the board, an infinite cone goes out forever this way and forever this way. So we're going out forever in both directions. All right, so that's what I mean by infinite cone. Okay. And we're going to take a plane. And again, an infinite plane. I'm just going to hold up a piece of paper. We're going to take a plane and we're going to cut this cone at various spots. And the intersection of that plane with the cone is going to create some image. And that image is going to be our conic section. All right. So those images are going to be different shapes, and it's going to depend upon how the plane cuts the cone. Now, it turns out that if we have a plane cutting a cone, the image of where the plane and the cone meet becomes our conic section. And it turns out that if you look at a two-dimensional rendering of that image on a Cartesian coordinate plane, then we can write every conic section algebraically as this, essentially a quadratic polynomial in two variables, x and y. So we have quadratic, meaning we're allowing squared terms, or we're allowing degree 2 terms. And then the A, B, C, D, E, and F, those are just real numbers. So algebraically, every conic section is going to look like that if we have to rewrite it. And the interesting conic sections are the ones where either A or C is non-zero, or both are non-zero. If A, B, and C are all 0, then we have a linear equation in 2. So if A, B, and C are all 0, then these terms go away and we just have a linear equation. So the non-trivial ones are where A and C or B is non-zero. And generally, what we do is we let B be 0 most of the time, because if B is not, then we can do a shift. of our cone. So what are we going to do with conic sections? Well, one thing we're going to do is we're going to identify some key components of each type of our conic sections. Second, we're going to create equations. So I'll give you some key parts to a conic section, and then we'll figure out equations from there. And then at the very end, we're going to take equations and we're going to say, well, this equation looks this way. Therefore, what conic section am I dealing with? So let's talk about some conic sections. We're going to start with a circle. I'll draw a depiction of a circle, but all circles can be rewritten in this way. X minus h quantity squared plus y minus k quantity squared equals r squared. The hk is the center of the circle. Hopefully this reminds you, if you dealt with pre-calc here, that's a shift. And then we have radius r. Let's check that out via Desmos. So here we have, here we have a circle centered at 0, and the radius is 5. It's x squared plus y squared equals 25. If I shift by doing x minus, let's say, h squared, we'll add a slider for h, and then do a y minus k squared, add a slider for k, and then do, let's just say r squared, and add a slider for r. Let's start with k of 0, h of 0. So right now, I'm centered at the origin. If I start increasing my r, notice that that increases the radius. So an r of 4 gives me a radius of 4. R of 5 gives me a radius of 5. All right. I'm sorry. Let me do something as well. All right. Hopefully we all know what a radius is. Radius is always the distance from the center to the outside edge. So no matter where this point is on the outside edge, it's a distance of r away. By distance of r, I mean, so here's our center, here's our outside edge. And we just move that point around. Oops. And you can see the radius. If the radius obviously were to change and shrink, right? No matter what location, no matter what point we're at whatever or however far away from, in this case, the origin. And then the HK, those are just shift. If I shift the H over or shift the K over, it just moves the circle. The minus K moves it up and down. The minus H moves it left and right. Okay. So there we can see the key components of a circle. Center is at HK with radius R. By the way, other things that sometimes people talk about with the circle is a diameter. A diameter is just twice a radius. It's from point to point through the origin, which means it's twice the radius. So remember, the first types of questions that we are asking are questions about, can we find certain features of a circle or any conic section, but in this case, we're dealing with circles. So can we find the features? Well, as far as the features go, center, radius, and diameter are about the only three that in this class we're going to ask for. So let's do center and radius of this circle. This will be easier, just try to type into Word rather than trying to draw on the board since the camera's down. So remember, the center is HK if we're in this format. Notice that already we are in that format. So because my circle starts in the format that I like, I can immediately read off that the H must be a -9 and the K must be a +4. Be careful about that. A lot of times people will mistakenly put a +9, but the format is X minus H squared, Y minus K squared. And then the radius is going to be R. And if I know R squared is 121, then I can take a square root of both sides. And radius is always going to be a positive number. So radius is going to be the positive square root of 121, which is 11. So that's how I'm getting the radius. Now that was all really nice because my circle was in this standard form of a circle. So it was already in that standard form. So it's pretty easy to read things off. we'll see some examples later if we're not in standard form, but we'll do that later. So that's one thing. For one type of question, identify key components of the circle. The second type of question is create equations of conic sections. So in this case, we're going to create an equation of a circle. And it says, find the equation of the circle with the following properties. Endpoints of a diameter are 8, 3, and 8, 9. Now remember, a diameter goes through the center of a circle. Let me try to draw that as best I can. Normally I would do it on the board, but let's see if I have a Microsoft Paint app that I can just pull up. Got it. Let's see if I can do it here. Actually, I got these tools. Might as well use them, right? So we have a circle. And 8, 3, and 8, 9. Well, those are going to be points on the circle. And because they are bigger. Eight, 3, and 8, 9 are situated at opposite ends because they're endpoints of a diameter. Not doing very well. And 8, 3, 8, 9 are vertically there. So where's my center? It's right in between. It's the midpoint between 8, 3, and 8, 9. Hopefully that makes sense. Okay. So center is the midpoint. By the way, to find the middle, if I wanted to by hand, for the x value, I just take halfway between the two x values. 8 plus 8 over 2 is just 8. Halfway between 8 and 8 is 8. And then I'd go halfway between the y values. 3 plus 9 over 2 is 6. So the center is at 8, 6. The radius is the distance between the center and a point on the circle. Doesn't matter which point we use, since the center is 8, 6 and the endpoints are 8, 3, and 8, 9. It's pretty obvious that the radius is 3. To go from 3 to 6, or to go from 9 to 6, or 6 to 9, the radius is 3. We can get that through common sense. Also, if our x values were not the same, we could get the distance by doing the distance formula, square root of x1 minus x2 squared plus y1 minus y2 squared. It doesn't matter which subscript you put first. You can go x2 minus x1 or y2 minus y1 if you like. So the distance formula is that one. And what I'm saying is that in this case, the x value from the center to an endpoint is from 8 to 8. The y values from the center to an endpoint, it's either 6 minus 3, I'll do that, or 6 minus 9, doesn't matter. You're going to get 3 squared there. This one's going to become 0. And you just end up with the square root of 3 squared, which is obviously just 3. So if you wanted to use the distance formula, obviously this one's easy just to see, oh yeah, distance is 3 from this center to the ends. Now that we know the radius is 3 in the center, now we can write the equation. Remember, it's x minus h, quantity squared, plus y minus k, quantity squared is equal to r squared. And I would take that equation and I would say, well, since the center is hk, replace the h with the number 8, replace the k with the number 6, and then the radius is going to be 3. 3 squared is 9. So the standard form of the equation for the circle is going to be x minus 8 squared plus y minus 6 squared equals 9. That's our standard equation for that particular circle. So with circles, if I have the standard form, it's pretty easy to read off the radius in the center. If I know the radius in the center, and I can find those things via all kinds of different methods, but as long as I know the radius in the center, then I know the equation of the circle. Now, our next conic section that we're going to look at is a parabola. And the standard version of a parabola is going to be actually one of these two. We're going to have x minus h squared equals 4p times the quantity y minus k. Or we're going to switch the roles of x and y by doing y minus k squared equals 4p times the quantity x minus h. Now, I'll talk about the vertex and the focus and the directrix in a moment, but for right now, just write down this information. When we have one of these two standard forms, our vertex is going to be h comma k, So it's going to be a point H comma K. Our focus is going to be P units from the vertex. And our directrix is going to be P units from the vertex as well. We'll talk about what the focus and the directrix are in just a moment. All right. So what you're seeing here, let me what you're seeing here is the parabola y squared equals negative 12x. Now, let me just write a different parabola, a few different parabolas. If I do x minus 2 squared is equal to 12, y minus 3, you see that when the x is being squared, when the x part, I should see, is being squared, this parabola is pointed up. If I throw a negative in front of that 12, all of a sudden the parabola is pointing down. The vertex is, when the parabola is pointing down, is this uppermost point on the parabola. When the parabola points up, and this is what I call pointing up, the vertex is the bottommost point on the parabola. Notice it's 2, 3, because I had x minus 2 and y minus 3 in for my x and y values. Now, if we switch the x to a y and switch the y to an x, now all of a sudden the parabola is pointing to the right when this number is positive. And when this number is negative, the parabola is pointing to the left. And obviously, this switched because now the y value is being subtracted. The 2 is being subtracted from a y value. So we can see that 2 is on the vertex. So the vertex is the leftmost or rightmost point. Hopefully you can see that that means in this top one, the parabola is pointing up or down anytime we have this form. And it's pointing up when P is positive and pointing down when P is negative. If we have this form, then the parabola is pointing left or right, and it's pointing right when P is positive and left when P is negative. The vertex is always the sort of turning point in the parabola, and it's going to be either the highest or the lowest or the leftmost or the rightmost point on the parabola, depending on how it points. Now, I want to explain what the focus and the directrix of a parabola are. And so I'm going to go back to my original parabola. This is a parabola pointing left. P here is -3 because -12 is -4 times P, so P is -3. Or 4 times P, so P is -3. So it's a parabola pointing left whose vertex is at the origin. Now, because P is -3, I called it A here. We have two objects. One is a point. This point is the focus. It is -3 units away from the vertex. The directrix is also 3 units away from the vertex, but in the other direction. And you can see that the directrix is actually the entire line. So the directrix is the line, in this case, x equals 3. Now, here's the interesting part. Let's say I take a point on my parabola. And I look at that in comparison to this line and in comparison to this point. So I look at it in comparison to the focus and in comparison to the directrix. Let's check out what is that point right there at this point in time. It's -3.6. I want you to notice that if you measured up 6 units from the point, from the focus, you'd get to that point. If you measured 6 units to the right, you'd be at the line. So this point, -3.6, is equidistant from the focus and from the directrix. I have everything turned off. Hopefully I didn't kill anything. Now watch what happens. As this point moves over and over again, all throughout the parabola, no matter where I'm at, let's say I'm at this point now, the distance from the point to the focus and the distance from the point to the directrix, I actually calculated those. No, I don't see it. Those two values are going to be the same. So this distance and this distance are the same, no matter where I'm at. Let's say I wanted to stop here. There you go. These two distances, the distance from the focus to a point And the distance from the directrix to a point on the parabola are going to be the same, no matter where the point is at. Okay. The other nice thing about the focus is that it turns out the angle of every parabola, if I have a object that comes into my parabola and hits the parabola. So let's think of this as a physical object. It turns out if it comes in this direction, hits the parabola, it's going to bounce back and hit the focus. So that's another nice feature about the focus. And that feature, if we come into the parabola this way, so some object hits the parabola, and I know it's going to bounce. And go right to the focus, that actually allows us to build nice satellites. The receiver for a satellite is going to be where the focus is. And so a satellite points up into the air, and whatever gets hit bounces off the edge of the satellite, goes to the focus. All right. Oh, get that off. Thought I did that already. Good. Now, that's a lot of stuff. Algebraically, what are we going to do? Well, we're going to do the same things we did with the circle. We're going to find some key features of the parabola, and then we're going to construct the equation for a parabola given some key features. Let's start with the first. Let's say I want to find the vertex, the focus, and the directrix of this parabola. Now, obviously, this parabola is not in the standard form. Previously, when we had a circle, it was already in the standard form of a circle. Now we have a parabola, but it's not in the standard form. So the goal is to get this into standard form before looking for the vertex, the focus, and the directrix. Now, how do we get this into standard form? The first thing we have to recognize is that the y component is being squared. So we'd like to get this standard form, the one where the y part is being squared. All right. So that means I need to manipulate this original equation given into this standard form. Notice that on the left-hand side, we have a squared piece with y and nothing, no other parts. So all the x's are on the right. So that's what I'm going to do. So what I do is say, take my equation, and I would subtract x from both sides. At this point, I am going to complete the square. So that I can get a square part on the left. That was silly. Hopefully you remember how to complete the square. We want something squared. So what we do is we see that the coefficient of my, well, first off, the coefficient of my x squared term, or my, in this case, y squared term is a 1. That's what I need to have. If it's not that, then I divide everything by that coefficient to get a coefficient of 1. So I know it's going to be y plus or minus some number. We'll call this number n for right now, squared is equal to something. Now, whatever this number is, this number here has to be half of my coefficient on my y. So it's got to be half of 1. And since that's a positive 1, half of 1 is 0.5. Then I square the 0.5. And get 0.25. When I add 0.25 on the left, I'm going to have to add 0.25 on the right as well in order to maintain balance. All right. So let me just explain what I did there. So I took the 1 and I went half of the 1. And then I took the 0.5 and I squared that. That's what I'm doing. So half of this coefficient goes into there, and then I square it, and I add it to both sides. And that's it. I get y plus 0.5 squared is equal to negative x plus 0.25. Now, I'm not quite done yet. I have the left-hand side the way I want it. The right-hand side, I need to have x minus h, not negative x plus a number. So what I'm going to do is I'm going to factor out on the left, excuse me, on the right-hand side, a negative 1. Now that I have my standard version of the equation, I can just read off a few things. Now, before I do that, I just want to be very, very clear. 4p in this version is -1. So that means the p there is -1/4 or -0.25, however I want to say it. So now that I have the standard equation, the vertex I know is 0.25 as far as what's being subtracted from x. So it's 0.25 comma -0.5. Because remember, this should be y minus k in the standard form. So that's a -0.5. By the way, because y is being squared, I know my parabola points left or right. And because the p is negative, I know it actually points left. So I know it points left or right because the y component's being squared and p is negative. So now I know the vertex, and the focus is p units away. From the vertex. Since it's pointing to the left, my focus is going to be p units away to the left. Hopefully that makes sense. So the focus is, we start at the vertex, and if we're moving to the left by 0.25, we're going to be subtracting 0.25. From the x component of the vertex. Hopefully everybody, that makes sense. So the focus is actually going to be at 0, comma, -0.5. Whoops, I don't have my decimal there. 0, -0.5 is my focus. Hopefully that makes sense with what I'm doing. I know it's pointing to the left, and therefore the focus is going to be in here somewhere. So I need to shift it over from the vertex. Shifting it to the left is a shift in the x component. Now the directrix is going to be a vertical line because the parabola is pointing left. So if the directrix is a vertical line, it's going to be x is equal to some number. Well, what number does it have to be? Well, it has to be the x value of 0.25 that is on our vertex. And then I have to add 0.25 to it. So the directrix is going to be the vertical line, x is equal to 0.5. Remember, all vertical lines have equations x equal to a number. All horizontal lines will have equations that look like y equals some number. So there you go. I can always clear this out, or excuse me, I can always check this out. If I want to, by going to something like Desmos and graphing that original equation, y squared plus x plus y equals 0. Let me actually start something. And sure enough, if I look at my vertex, it's at 0.25 comma negative 0.5. Just like we had. And it looks like my focus should be, I can just graph this, at 0 comma negative 0.5. And my directrix should be x equals 0.5. This green line here. And if I took any point, it would be equidistant from the focus to the directrix. So that looks right. That doesn't guarantee it is, but it looks right. So we did that all algebraically using completing the square. That's how I would expect you to do it. I don't think graphing every time is good, because on the test you won't have access to Desmos. You'd have access to your calculator, but turns out your calculator doesn't graph this well. So that's finding the vertex, focus, and directrix of a generalized parabola and having to complete the square to get our parabola into a form that we can recognize. I want you to take a moment and do the same thing with this parabola. X squared minus 2x plus 8y plus 9 is equal to 0. All right, so let's take a look at this one. We're going to do very similar things that we did last time. And we'll get all these same things. So, first off, I should recognize that goal is to get standard form. The x is being squared. So the standard form that I'm looking for is x minus h squared is equal to, 4p times y minus k. That's because the x part's being squared. So I'm going to get the x squared minus 2x on one side, and the other side I'm going to subtract 8y from both sides and subtract 9 from both sides to give me minus 8y minus 9 on the right. Now, in order to complete the square, I'm going to take half of negative 2 and put it in here. And then square negative 1. If I square negative 1, I have to add 1 to the left side. And if I add 1 to the left side, I have to add 1 to the right side. So I'm adding 1 to both sides in order to complete the square. We're one step away from getting this into standard form. Since I have negative 8y, I'm going to factor out a negative 8. And that gives me negative 8 times y plus 1. Now, this also means that my 4p is negative 8. So that means p is negative 2. Since x component is being squared, this means I'm going to be pointing down. Since we have this standard form, x minus 1 means the vertex is going to have x value of positive 1. Since I have y plus 1, that means the y value of my vertex is going to be negative 1. Focus is p units away. That's negative 2 units away. But remember, we know that we're pointed down. So my focus is going to be down 2. Down means I'm changing the y value. And then my directrix, I'll draw that, is going to be above by 2. So to get the focus, I'm going to start at the vertex, and then I'm going to subtract 2 from the y value. So my focus is going to be 1 comma negative 3. I went down 2 units from where the vertex was. Similarly, notice that my directrix is a horizontal line. So my directrix equation is going to be y equals some number. And that number is going to be 2 units up from my vertex. So I'm going to take my vertex y value and add 2. That means the directrix is y equals +1. So once I complete the square, I get my equation in standard form. Then it's pretty straightforward. I read off the vertex. I first off decide maybe whether or not we're pointing up, down, left, or right by which part's being squared and the negative or positive of the p. Once I do that, read off the vertex, and then I decide whether the focus is going to be up, down, left, or right. If it's up or down, I'm changing the y value from the vertex. If it's left or right, I'm changing the x value from the vertex. And the same thing with directrix. If my directrix is horizontal, then I'm changing the y value of the vertex, and my directrix is going to be the line y equals something. If my directrix is vertical, then I'm changing the x value of the vertex, and my x equals something is going to be the line. Hopefully that all makes sense. So that is how we complete the square to make things into standard form. And then once things are in standard form, I figure out the properties of the parabola. Remember, the other type of question that's going to be asked is if I give you some properties, let's find the equation of the parabola. And that's this example, example 5. Find the equation of the parabola with the following properties. The vertex of the parabola is the point 5,4, and the focus of the parabola is the point 3,4. Okay. Now, typically what I do is I draw the 2 points. If we're thinking about what a parabola looks like, whose vertex is 5, 4, and whose focus is 3, 4. Well, if the focus is to the left of the vertex, straight to the left, then that means the parabola has got to point left. Okay. So since the parabola points left, we're going to be using the one where we take y minus k squared equals 4p times x minus h. Since the vertex is 5, 4, I know the H is going to be 5 and the K is going to be 4. Now, what about the P? Well, P is the distance from the vertex to the focus. So in this case, it's pretty easy to see. There's only the X value changes. So the P is 2. Oh, actually, I'm sorry. The P has got to be -2, right? Because we're pointing to the left. If we were pointing to the right, it would have been +2. But P is -2 since we're pointing to the left. And what's that mean? That means that our equation, in order to find it, we just have to substitute in a P of -2. And it's that. Y minus 4 squared is equal to -8 times X minus 5. Now, obviously, we have to, figure out what the vertex is and what the P is to be able to do our parabola. And so sometimes that's harder, sometimes that's easier. Here we were given the vertex, and even though we weren't given the P, it was a straightforward subtraction to get the P value. Obviously, there's other techniques that could be more or less difficult. I want you to try this one on your own. Take a couple of minutes to find the equation of a parabola with the following properties. The directrix is x equals -2, and the focus is the point 3, 4. I always suggest kind of drawing a little junky picture to see which equation style you're going to use and whether the P is going to be negative or positive. And hopefully you can do that based off the picture. All right, so let's go ahead and do this one. The directrix is x equals -2. The focus is 3, 4. Okay. Now, the first thing I always do is figure out which equation I'm going for. The one where we're squaring the y part or the one we're squaring the x part. And to do that, I just draw a crappy little picture of the focus at, let's say, 3, 4. So we have this focus here at 3, 4. And if the directrix is at x equals -2, that means the directrix is going to be to the left. Well, first off, x equals a number is a vertical line. And if the focus here is at 3, 4, and the directrix is at x equals -2, then the directrix is to the left of the focus. So it looks like here we're pointing to the right. And that means we're going to have this equation again. But this time we're going to have a positive p-value. Now, what is the vertex in this case? Well, it's between the focus and x equals -2. It's got to be equidistant. And so notice the height of the focus and the vertex are going to be the same. So the vertex is going to have y value of 4. But the vertex is going to be in between x equals -2 and an x value of 3. So the x value is going to be halfway in between -2 and 3, but the y value has to be 4. If we calculate that, obviously the y value is 4. -2 plus 3 divided by 2 gives you 1/2 or 0.5. So it's 0.5, 4. So x minus 0.5 and y minus 4 are going to be those two components in our equation. We're going to keep those there the whole time. All right. Now, what's the p? Well, the p is the distance from the vertex to the focus. If 0.5 is the x value of my vertex, to go to my focus, 0.5 to 3 is a p-value of 2.5. And it is going to be positive because we're pointing to the right. It's also the distance from the vertex to the directrix. So 0.5 to -2 is also 2.5. And again, we're talking about a positive p-value. And that means when I take 4 times p, I'll get 4 times 2.5, which is 10. So the equation that I'm looking for is y minus 4 squared is equal to 10 times the quantity x minus 0.5. And there you go. Again, it's sort of a combination of using our knowledge about how the equation looks in comparison to the vertex and the P, and also using some common sense about what the what the actual parabola looks like when you graph it. So it's a combination of the graph of the parabola along with the equation and how those things interplay. But there you go. Again, this is not the only way we can find parabola, find a parabola, but when you're finding parabolas, finding the vertex, finding the P, those are the two big pieces. Now, the next conic sections are ellipses. Just like the parabola, there's actually two different equations for ellipses. One has x minus h squared over a squared plus y minus k squared over b squared equaling 1. By the way, these are the standard forms. The other has x minus h squared over b squared plus y minus k squared over a squared equals 1. So the difference in the two equations is whether the a squared is underneath the x part or whether the a squared is underneath the y part. And we note these by what's the bigger of the two values. A is always going to be the bigger number compared to B. A and B are both going to be positive always, but the two are going to be different in size. And what this gives me, try to go to Desmos. What this gives is a shape that looks like, well, here we have a circle. Why do we have a circle in this case? Well, we have a circle in this case because A and B are the same. However, if A starts becoming bigger, then we have stretched that out. We stretch that out along the x-axis. So as A keeps getting bigger. Now, what if the number underneath the y had become bigger? Well, if the number underneath the y had become bigger, then we would have stretched it out along the y-axis. When they're equal, we get a circle. But when the number under the x is bigger, it's elongated this way, left and right. When the number under the y is bigger, it's elongated up and down. And we can elongate, quite a far, long way. So that's what the graph of an ellipse looks like. Again, it's a conic section. And that's the graph. Now, there's some components of an ellipse that you should know. Now, remember, my equations had A as the bigger value. So if the A is underneath the X versus the A underneath the Y, the center of the ellipse is HK. The length of the major axis is going to be double A. I'll show you what that looks like in a picture in a moment. The minor axis is length 2B, so double B. There are actually two foci. Foci is the plural for focus. And they're both going to be on the major axis. They're going to be C units from the center. And with an ellipse, you can always find that C by using the following formula. C squared is equal to A squared minus B squared. Since A is always bigger, C is going to be the positive square root of that thing on the right. And then there's something called eccentricity, which basically tells you something about how close to a circle versus how close to a parabola it looks like. In other words, how stretched out it is. The closer to 0, the closer to a circle we're going to have. The closer to 1, the more stretched out it's going to look. So the things we're going to find on an ellipse are these features: the center, the major axis, the minor axis, both foci, and the eccentricity. Again, eccentricity is just a numerical value. For an ellipse, it's always going to be between 0 and 1, and it tells us how stretched out the ellipse is. Now, let me talk a little bit through an ellipse. So here's an ellipse which I've created. Let me mark all these things off yet. As you can see, it's stretched out vertically more than it is horizontally. It's stretched out more vertically. I have centered it at the origin just to make everyone's life easier. And you can see that underneath the y squared is the number 25. So that means the b is 5, right? 5 squared is 25. And you can see that if you go from the origin to this point over here, that's a measurement of 5 units. Let's go by steps of size 1. There we go. By the way, this uppermost point of the ellipse, that's called a vertex. And the ellipse always has 4 vertices. The upper and lowermost points and the left and rightmost points. By the way, since we're on the origin, it's pretty easy to see. We went 5 units up, 5 units down. And also, notice the number under the x squared is a 16. We've went 4 units to the right, 4 units to the left to get our vertices. So the vertices are just left, right, however many units in the x direction, up, down, however many units in the y direction. Now, for us, c squared is equal to a squared minus b squared. A squared in this case was 25. B squared in this case was 16. So c was 3. That means I'm going to have 2 foci. 3 units from the center. Now, what's the interesting feature of these 2 foci? Why do we even call them focus? Why do we even call this one and this one a focus? Well, the interesting feature is that if you put a point on this ellipse and you let it move around the ellipse, the distance from this point to one foci and the distance from this point to the other foci are going to be changing. In fact, right now, at this point, so right now, at this point, it's obviously much closer to this upper focus than it is to this bottom focus. But if you add these 2 distances up, you actually get a 10. So the distance to the upper focus is about 3.106. The distance from the point to the lower focus is about 6.894. Adding those 2 distances up gives me a total distance in green of 10. Now watch what happens if I move the point around. Let's say I move that point to here. The distance to the upper focus now is about 5.42. The distance to the lower focus is about 4.58. But the sum of the 2 distances is 10. Notice that as the point moves around and around the circle, even though the 2 individual distances change, the sum of those 2 is still 10. So that's the geometry feature about an ellipse. That's nice. That no matter what point we're dealing with on the circle, if I take the sum of the distance between the point and the first foci plus the distance between the point and the second foci, we're always going to get a constant number. In this case, it happens to be 10, but it doesn't always have to be a whole number or anything like that. I just made my life easier by using 25 and 16. So that's the interesting geometrical property about the ellipse. The sum of these two distances is constant. So now that we see that, we can find information. The only other information I didn't put on this sheet, and it kind of goes into this major axis length, minor axis length, is that there's vertices along the major axis, and they're A units away from the center. There's vertices on the minor axis, they're B units away from the center. So let's do one example here with a standard equation of an ellipse. I'll go right into it. So we want to find the center, the foci, the vertices, the eccentricity of this ellipse in standard form. So the A is under the Y part because that's bigger, right? 25 is bigger than 16. A is 5. B is 4. Just the square root of 25, positive square root of 16. So let's start by finding the center. Center is HK. The X is being, well, it's X minus 3. So that's going to be a positive 3. Remember, it's always X minus H. And then Y minus 1 means the Y value of the center is positive 1. Oh, because the bigger number is underneath the Y, this is going to be stretched out vertically more than horizontally. So the ellipse stretched vertically. So that means the vertices we can find by adding 5 in the Y value to the center and subtracting from the Y value. So I'm going to take the center and I'm going to add 5 because, again, 25 is under the Y part. That's going to give me the upper vertex. And in order to get the lower vertex, I'm going to take 3, 1, and I'm going to subtract 5 from the Y value. So my lower vertex is going to be 3, negative 4. Upper vertex is 3, 6. The right left vertices, I'm going to adjust the X value. So we're going to take 3 plus 4 comma 1. That's going to be my right vertex. So my right vertex is going to be 7, 1. And my left vertex is going to be 3 minus 4, comma 1. So my leftmost vertex is going to be negative 1, comma 1. So that's the center, 3, 1, and then the 4 vertices. Now, by the way, an ellipse is always going to have an upper, a lower, a left, and right vertex. Now let's talk about the foci. In order to do this, c squared is equal to a squared plus b squared. A in this case is 25. I'm sorry, a squared is 25. I mistyped this. For an ellipse, it should be a squared minus b squared. Oh, let me repeat that. C squared is equal to a squared minus b squared for an ellipse. That means when it's all said and done, C has to be 3. Now, the foci are going to be along the major axis. So we need to vertically shift by 3. So we're going to have an upper and a lower foci, or upper and lower foci, focus, an upper focus and a lower focus, or 2 foci. 1 is upper, 1 is lower. So again, I start at the center, and I'm going to shift up by 3 units to get the upper focus. So my upper focus is at 3, 4, and my lower focus I start at the center and I shift down by 3. So my lower one is going to be 3, comma, negative 2. And again, it'll be here and here, somewhere in there. Lastly, the eccentricity. Once you've found the eccentricity, sometimes you call this E. That's not, but it's C over A. So it's pretty easy. We found C is 3, A is 5. So the eccentricity here is 0.6. This same C, this same A. So it's 0.6. And again, that's just a number to tell me how stretched out my ellipse is. Next class period, we'll keep going in this. Hopefully the projector is fixed by next class period. But we'll see. All right. I'll see you next time.